So, all right. Lecture 6-7, proportional lead design. Similar to how proportional lag controllers can be considered passively realizable PD controllers, PI controllers, this is exactly opposite. That's nice. PI controllers, proportional lead controllers can be considered passively realizable PD controllers. It's a really good start. Okay. The idea is to choose a design point psi through which we construct the root locus to pass. As with PD control, this point is chosen to meet primarily transient response characteristics. And the controller contributes the proper phase such that the root locus passes through the point. However, we have both a pole and a zero to set in the proportional lag, or in the lag compensator. So we've got a zero to place and a pole to place. We will arbitrarily choose either the pole or the zero, and the phase criterion for our design point psi will set the other. Okay? Now, why did we not have this situation? Why didn't we have to arbitrarily choose one for a derivative controller? We were only adding the zero. So we only had one location, and that was determined by the phase criterion, effectively. So now we've got two, and we want to do the same thing with it. So we have two parameters, and there's really only one constraint on them. So we get one that's free, and the other one is determined. However, the arbitrary selection of PC or ZC, and we are air quoting arbitrary because it's only kind of so, in fact affects both the transient response and the steady state error if it is finite. Of course, if it's zero steady state error or if it's infinite steady state error, then that's not going to be affected by the specific locations of these poles and zeros. But in the case of a finite steady state error, the location of the poles and zeros is going to affect the steady state error. And recognizing that's important, even though we don't necessarily spend a ton of time worrying about it at this point, because we can always put in a lag compensator if we want to, or an integral compensator. You don't really see a lot of mixing and matching of lag and lead with integral and derivative, because they're sort of on like two different sides. If you're going to do integral, you might as well do derivative. If you're going to do lag, you might as well do lead. So they kind of stay in their own silos. So even though it's not what we're using our design to do, like we're not using a lead compensator to improve steady state error, realize that our free parameter does affect steady state error, and so choosing it accordingly can be helpful. So we're actually going to explore that a little bit in an example that we do. What happens to for your choice of your arbitrary one? Okay, good. So let's work out the details. A way to approach designing a controller for a plant G with lead compensator C is to consider the compensator effects on the phase criterion, which must always be satisfied at points on the root locus. So we know that the phase of the plant multiplying the controller has to be equal to pi. In order for a desired point S to be on the root locus, then we have to have the I forgot to print out my notes on this subject. So pardon just a moment while I look for that equation. Yeah. Okay. So just want to remind myself of what I do here. Okay. So we've got essentially a plugging in of the point psi into our phase criterion for S. And we say that has to be equal to pi. And we're suppressing a 2 pi modulo here, right? Because it has to be equal to pi, or 3 pi, or 5 pi, 7 pi, etc. 2 pi increments. And this, remember that phases add when we multiply the complex components. So we've got the angle of g of psi plus the angle of c of psi equals pi. And that allows us to solve for the angle of c of psi, which is equal to pi minus the angle of g of psi. And for the controller that we're going to have here, for this compensator in this case, we're going to have the phase of psi minus zc minus the phase from the pole. This is the phase from the 0. This is the phase from the pole. Pole is from the denominator, so it's subtracted of the compensator. Pi minus angle g of psi. And this is very similar to what we did for the derivative controller, but for the derivative controller, we only had this angle of the 0, right? We didn't have the pole contribution. So that's why we've got two things to work with, but we just need their difference to equal pi minus g of psi. So let's call this the compensator angle and be given by the symbol theta c. So we can choose to arbitrarily set the location of either zc or pc, and the other will be set by the phase criterion. Therefore, we have either arbitrarily setting the 0 location and computing what theta c has to be and finding out what our phase of our pole must be from that. Or if you want to set the pole location, then you have this relationship here, which is just these two equations, 6.37, are just the consequence of this relationship here. But how we'll use them is we'll say, okay, we'll say zc, we'll set arbitrarily. Theta c, we know from our psi point what that should be, and we will therefore compute it from here, and then we will compute either our pole angle contribution or our 0 angle contribution. And from trigonometry then, if you know the angle, you can back out what the pole and 0 locations must be. So I just work that out in either case. So if you want to set your 0 location arbitrarily, this is what your pole location should be. And if you want to set your pole location arbitrarily, this is what your 0 location should be. So this result is to be used in the design procedure that follows. So it provides a starting point for proportional lead controller design. Let's assume the transient response requirement is such that, according to the second order approximation, we desire a closed loop pole to be located at psi. First, design a proportional controller to meet transient response requirements by choosing the gain for the dominant closed loop poles to be as close as possible to psi. So you're just trying to do proportional control, but we know that we're not going to get where we want to go exactly. So then we include a cascade lead compensator, step 2, of the form given here, where we arbitrarily set either z, c, or pc, initially setting the gain to 1, The other parameter must be chosen to satisfy 638A or 638B, depending on which one you choose. For convenience, we repeat the key formulas here. Theta C is the same in either case, and if you set ZC, then you're going to want this PC formula. If you set PC, you're going to want the ZC formula. And that's how you find your compensator. And then by construction, so we could build another root locus, right? And then, find, oh, look, our design point is on the root locus. That's great. It's good to check that. But if we did it correctly, then the gain can be computed directly from equation 6.2. And we compute it to be this. This was from the first lecture in this chapter or the second lecture. But it had that analytic gain value. Remember we talked about that the other day, and I said, if you want to find that gain analytically, if you know a point on the root locus, psi, this is where we're using it. We also used it in the PD design. 4, construct the closed loop transfer function with the controller given here. So you have your K1, your K2, and simulate the time response to see if it meets specs. Tune accordingly. So this is our process. Any questions on that before we do an example? I think I'll split the example off. It's going to be a little lengthy.